Cosmology has changed forever with the launch of James Webb on Christmas Day, 2021. Ever since it opened its impressively sharp high-resolution infrared eyes, James Webb looked back at some of the earliest stages of the universe, gathered sharp, pristine, and beautiful insights of early star and galaxy formation, and provided insights into the formation of planetary systems, including our own solar system. But in some sense, James Webb was almost too good, far exceeding all hopes and expectations. Astronomers expected to find some of these infant galaxies with Webb, but they didn't expect to find so many. Webb's unprecedentedly deep views revealed a colossal surprise, a bunch of the impossible early galaxies. Even at these earliest times, these galaxies were too big, bright, and numerous to explain, some of which are even older than the universe itself. Our best cosmic predictions, based on lambda cold dark matter, the standard model of cosmology, didn't expect what James Webb saw. In other words, discoveries made by James Webb could shake our understanding of galactic history, as well as the Big Bang and all of modern cosmology. Join us as we dig deep into how James Webb just found massive structures that could defy our current theories of the universe. The farther and farther back into the distant universe we look, we have a picture of what we expect to see. At some point, we should find the first and earliest bright, large, luminous galaxies, and we should see their number density rapidly decrease as we approach that limit. Before that, we should find only smaller and less evolved galaxies, decreasing in number and number density until we find the very first among those. Before that, we should only see individual star clusters and protogalaxies, and these should be extremely blue and primitive and, again, should only exist in low number densities. Finally, there should truly be a time where the very first stars and star clusters have all appeared, and beyond that, there should be no luminous sources at all to observe except the Big Bang's leftover glow itself. When we look into these deep depths of the universe and examine these galaxies, we are basically asking the universe, how did you grow up and come to be the way you are today? Given that we have a model of the universe, a mix of dark matter, normal matter, dark energy, and a little bit of radiation, we can arrive at predictions for what we expect to see in the universe at any given time. Looking at these distant objects with the James Webb Space Telescope, and with its spectroscopic capabilities in particular, allows us to test that model and to see if we truly understand the universe we inhabit, or if and how we have to revise our picture of the cosmos. The James Webb Space Telescope is changing astronomy in many ways, from peering into the atmosphere of exoplanets to capturing stunning images of distant cosmic phenomena, but perhaps its greatest scientific contribution is its ability to observe galaxies that are so distant that looking at them is like looking back in time. Projects like Webb Sears, or Cosmic Evolution Early Release Science Survey, are scanning the sky to pick out some of the oldest galaxies we've ever seen. When scientists first turned Webb toward apparently empty patches of sky to look for these distant galaxies, they found something very strange. They didn't just find a few very old galaxies dating back as much as just a few 100 million years after the Big Bang. They found far more of these galaxies than anyone had predicted. According to Mela Bagley of the University of Texas, one of the leading Sears researchers, the theoretical models didn't predict that these galaxies should be there. We still don't yet know how you can see a galaxy that bright that early. One particular galaxy jumped out of the Sears data straight away, M's galaxy, named after the daughter of Stephen Finkelstein, one of the researchers. It is 13 billion years old, making it one of the oldest galaxies ever observed, and it is much brighter and much bluer than anyone predicted. As Bagley said, when we found M's galaxy, the surprising part was, how is it in the universe? It's exciting that this is the universe we live in. It's a universe with a ton more galaxies than we thought. Webb is able to detect extremely distant galaxies because its instruments operate in the infrared wavelength. A small handful of extremely distant galaxies had been detected previously by the Hubble Space Telescope, which operates primarily in the optical light wavelength, equivalent to what human eyes can see. But as galaxies move further and further away from us due to the expansion of the universe, their light is shifted toward the red end of the spectrum in a process called redshift. The extremely distant galaxies that early universe researchers are interested in have light that is redshifted so far that it is no longer visible in the optical and can only be seen in the infrared. So, Hubble's instruments were pushed to the limits to detect even a few of these galaxies, while Webb was able to detect many of them incredibly quickly, within a few days of the telescope beginning its science operations. When discussing these galaxies, scientists typically talk about them in terms of their age rather than their distance. You'll see researchers describe a galaxy as being from the first few 100 million years after the Big Bang, rather than being located billions of miles from Earth. That's also because of the expansion of the universe, which creates a moving frame of reference that makes it hard to describe distance meaningfully. Examples include galaxies like M's galaxy, which is described as being 13 billion years old. The light has traveled 13 billion years to get to us, but if we could see M's galaxy today, it is much, much further away because, in that time, the universe has kept expanding and accelerated its expansion. The time the light has spent traveling to us gives us more concrete information about when in the universe we're observing these galaxies. Initial estimations of the redshift, and thus the age of M's galaxy, were based on photometry, which works by analyzing brightness in images while using a small number of wide-frequency filters. These calculations suggested the galaxy had a redshift of 11.8. But Finkelstein and the Sears team wanted a more accurate age estimation. To do this, they made follow-up observations with James Webb's near-infrared spectrograph, or NIR-SPEC for short. This allowed Finkelstein and colleagues to look at spectral lines created in light data, dictated by the absorptions and emissions of chemical elements at specific wavelengths. From there, they could pinpoint the actual redshift of M's galaxy. It appeared to be 11.4. This means M's galaxy is technically seen more recently in the universe than initially estimated by a factor of tens of millions of years. Nonetheless, it is still considered immensely old. James Webb captured the galaxy as it was just 390 million years after the Big Bang. This impressive age places M's galaxy among the 4 oldest galaxies in the universe that have had their ages confirmed by spectroscopy, a technique that splits light into its component frequencies to better reveal its brightness, heat, and chemical composition. While such galaxies don't yet pose problems for leading models of cosmology, they suggest galactic formation began earlier and proceeded faster than expected in the universe, which theorists had previously predicted began churning out galaxies at the ripe age of 1 billion years after the Big Bang. As Fabiola Pacucci of the Harvard-Smithsonian Center for Astrophysics said, "We're seeing a rise of massive galaxies faster than we thought previously." The ages of some of these early galaxies were estimated at just tens of millions of years. This could have implications for large structures of dark matter, known as halos that sculpted early galaxies, and for the nature of dark matter particles themselves. One of the big open questions is, what is dark matter? Says Sandro Tecchella of the University of Cambridge. The first generation of galaxies is a sensitive probe for different dark matter models. On the other hand, we should be cautioned that some problematic and potentially model-busting early universe candidate galaxies still remain. Scientists had already produced models of what early galaxies would be like, and Webb contradicted them almost immediately. As soon as James Webb began looking for early galaxies, it found far more of them than anyone had predicted and found that they were much brighter too. Light is a double-edged sword in the context of these galaxies. It's what lets us study them, but there's so much more of it than astronomers would have expected. The brightness of a galaxy can be related to its mass, because a galaxy's light comes from stars. If you assume a certain average brightness and mass of a star, you can roughly estimate the mass of a galaxy. But much of the modeling astronomers have done up to this point has led them to believe that there wasn't enough time for galaxies to get this massive in so little time. According to Jorge Moreno, an associate professor of astronomy at Pomona College, it's like if you went to a kindergarten and you saw a teenager. What's more, today, most galaxies are separated into 2 types: spiral, which are disk-like with arms of dust and gas, and elliptical, which are more like spheres of smooth light. Until now, scientists thought that any galaxies from this relatively early period in the history of the universe would have been too young to have been forced into that binary yet. Instead, astronomers thought the galaxies would be blobs, but under James Webb's views, some of the early galaxies look a lot like galaxies in the local universe. They seem to have added structure and maybe even spiral arms. That wasn't something we really expected, Moreno said. The high level of structure and brightness in these galaxies is leading some astrophysicists to question the age of the universe in an attempt to explain the impossible. Massive galaxies existing so early in the timeline of the universe. A researcher has posited that the universe is roughly twice as old as previously believed. They push the age of the universe from a spry 13.8 billion years old to roughly 26.7 billion years old. The new estimates are based on the work of Rajendra Gupta, a researcher at the University of Ottawa. In a paper, Gupta details the challenge of explaining the existence of these early galaxies in the universe. He tries to justify his new timeline of the universe by referring to time dilation in the early cosmos, a period known as the Milky Way era, as one possible explanation for the seemingly impossible galaxies. However, most cosmologists have not accepted this explanation. As it stands, the discovery of early massive galaxies by the James Webb Space Telescope has far-reaching implications for our understanding of the cosmos, challenging our existing models and theories of galaxy formation and the age of the universe. The wealth of data gathered by James Webb continues to inspire new hypotheses and stimulate vigorous debate within the scientific community.